Okay, we're continuing on with parametric equations. This next example here, example 2, is going to take the problems or the equations from example 1, and we are going to write the corresponding rectangular equation to it. So basically when we're doing that, we are figuring out how to remove the parameter t. So we want the equation just with x's and y's. So typically we do it via substitution, okay? So here's what we know. If x is equal to 2 cosine of t and y is equal to 3 sine of t, okay? A couple things over here that I do want to make sure I don't lose track of. T itself is greater than or equal to 0 and less than or equal to 2 pi. Okay, I'm going to come back to that in a second. All right, I'm basically going to solve one of these, either the x or the y for t. I'll do the x equation. And when we solve for t, we do the inverse cosine on both sides, or arc cosine. And that will reverse cosine, leaving us with just t, okay? Now, let's think about this for a second. As t goes from 0 to 2 pi, cosine of t goes from -1 to 1. And if I multiply by a 2, that means 2 cosine of t goes from -2 to 2. Well, remember this was x. So x actually toggles between -2 and a +2. Okay, so if you remove the parameter t, what dictates the domain and the range? Well, we have to make adjustments for that by talking about what the x's and the y's are. So this is what I would claim is the kind of the span that x is allowed, or domain, right? If you decide that x's will be your inputs. Okay, and I kind of have decided that because to eliminate the parameter now, meaning to write this equation so that there is no t, then I'm going to substitute all of this into the t, our inverse cosine, x over 2. You can write it inverse with a -1 power, or you can write the word arc, same thing. Now, if you look at this equation, you will see there's no t in it. There's our domain. I could certainly talk about range also, because we know that the sine function only outputs between -1 and 1, and we are multiplying that by 3. So the y values, if we wanted to go one step further, we could talk about how this toggles between -3 and 3. Okay, so this right here is the rectangular equation. Parameter t is gone, okay? All right, let's go here. We're just gonna review this one more time, and then we'll get into some fun application problems. Okay, so same thing, graph it by hand. So we have a parameter t. It looks like t is gonna stay greater than or equal to 0. So when making my table of values, I'm going to continue on and not do any negatives, okay? X's are calculated by doing the square root of 2t. If I put in a 0, I'll get 0. If I put in a 1, I'll get root 2. If I put in a 2, I will get, you know what I'm going to do? I'm going to make some lines here. Square root of 4. Square root of 6, square root of 8, okay? The y's are going to be 4t. So 0, 4, 8, 12, 16, holy smokes. Okay, those numbers got big kind of fast. So if I come over here, and I'm going to plot these on my Cartesian coordinate grid, so x's and y's, this will be 0, 0. This will be root 2, 4. This will be 2, 8. This will be root 6, 12, root 8, 16. All right, I'm going to run out of space on my grid really quickly, I have a feeling. Here's my points. 0, 0. Root 2 is about 1.4. 4. 2, 8. Right? All right. Now, that was me graphing it by hand. And then it says, find the corresponding rectangular equation, which again is substitution of some sorts to get rid of the t. So I'm going to use this x and this y. I'm running out of room here. If x is equal to square root 2t and y is equal to 4t, technically it doesn't matter which one you solve for, but mental note here, if t is greater than or equal to 0, then the stuff underneath this is greater than or equal to 0, and square rooting it then is possible, and x will be greater than or equal to 0. Okay? All right, let's solve this for t. Square both sides, divide by 2. Substitute. Clean it up. We have 2x squared, where x is greater than or equal to 0. There's the rectangular equation and my domain. Real quickly, I didn't put any arrows on here to indicate orientation, so I'm going to go ahead and do that now. Okay. All right, let's talk application problems. This is, in my opinion, the fun part. Suppose you hit a golf ball, or you watch somebody hit a golf ball, right? What's happening when that golf ball is hit? Well, it obviously is moving away from the golfer, well, hopefully, right? And it is vertically moving up in the sky, in the air, and then it comes back down to the ground, okay? And then at some point when it comes back down to the ground, it stops moving farther away from the golfer, right? So there's two different things at work here. There is the height of the golf ball, and then there is the distance out from the golfer that the ball has gone. So we have a horizontal distance, the second one, and we have a vertical distance, the first one. So these two formulas, where t is the parameter, will give us a set of parametric equations to describe the path of the ball, both its height and its horizontal distance away, which is kind of interesting. All right, so number 4 says, if a golf ball is hit with an initial velocity of 150 feet per second, v sub 0, at an angle of 30 degrees with the horizon, means original angle, use parametric equations to describe the position of the ball. Now, since it says feet per second, I know that we're working in the standard measurement system, not the metric. So as far as gravity, we're going to use this 32 feet per second squared, not the 9.8 meters per second squared. Okay? So the height, which is the y value, is negative 1/2 gravity, which is 32. T is our variable, squared, plus v sub 0 is our 150 feet per second, sine of 30 degrees. So I'm going to have to come back and fill in what the sine of 30 degrees is here in a second. And behind all of this is the variable t plus h sub 0. Well, h sub 0 is the height at time 0. So really it's a plus 0 on the back end. We normally don't bother putting that. It's a golf ball. It's hit when it's on the ground. So this is a 0. I need one that describes the x, which is the horizontal distance. V sub 0, which is 150, I'm using this equation now, which is 150 feet per second, times the cosine of 30 degrees, and the variable behind that is just a t. So my x is going to equal 150 times cosine of 30 is root 3 over 2 t. So this is the answer to number 4. I know I kind of drug it on there in 2 different spots, but this one is the height, so vertical distance of the golf ball, and this one's horizontal distance of the golf ball, okay? When it says, now if we graphed this, I'm going to show you how to graph with your calculator also, but if we were to graph this and we had t working behind the scenes, we're going to have the height is changing, and we're going to have the horizontal distance changing, so the graph would look something like that, okay? When does the ball hit the ground? Well, here, right? That is going to happen when y is 0. So we're going to answer what t makes the y value 0, okay? And I can set this equal to 0, factor it, and solve. So what would this look like? This is going to look like 0 equals, I can take a t out of negative 16t plus 75. Well, I don't care about that 0. I know that that's t equals 0. How about this one? This t value is going to be 75 over 16 when you solve, okay? All right, I'm going to grab my calculator. So here's what I know. This y value and this y value happens when t equals 0. So here at this spot, t equals 0, obviously x is equal to 0 here, and y is equal to 0 here. Here, t is equal to 4.6875, x is equal to, we don't know, and y is equal to 0. The t is the time, so this is seconds, right? So when does the ball hit the ground? At 4.6875 seconds, okay? When is the ball at its max height? So what t is this one? A couple different ways we can find it. If you remember your quadratics, you could use your vertex formula. I know that we have a x-intercept here and an x-intercept here, so I can just cut them in half. So 2.34 at 2.34 seconds, okay? What is the max height? Well, I'm going to take my y equation and plug in 2.34. Now, I told you a moment ago that, so like this spot right here, t equals 2.34. X we don't know, y is what this one's asking. I'm going to show you on a graphing calculator how to enter parametrics, okay? Coordinates. So I'm going to go to mode. I don't want polar coordinates. So as you can see, I'm going to go down here, and I'm actually going to select parametrics. When I select parametrics, I now have an x with respect to t and a y with respect to t. Now remember, my x was 75 square root 3, come out of that. And when you hit that x value, it's going to put a t there, okay? Because it's x with respect to t. Now my y equation was negative 16 t squared plus 75t. I don't think I had anything else involved there. So let's graph it now and see. When we graph it, it's going to graph the relationship with x and y, and t is working behind the scenes, okay? I am going to change my window though, because we already know to 700. Let's see what we get. Oh, there it goes. Ball comes up, ball comes down. Okay, now I need to also stretch my y max. Yeah, that's a good. I'm going to change my y max again. I don't need to go as high. So I'll go 150. There. Look at that. Graph goes up, graph comes down. Yeah? All right, so t is not on here. T is working behind the scenes. If you go to second and table, you will see that you're at time 0, your x is at 0, your y is at 0. But at 1 second, the x, the horizontal distance that it is away, is 129.9 already. And this vertical height above the ground is 59. Now, this was in feet, right? So these are both labels in feet, okay? The interesting one here is that somewhere between 4 and 5 is where we have the vertical height hits a 0, which we kind of knew already because equation, that's where we have it coming down and hitting the ground, okay? All right, so let's find some values now that we have a graph of it. Max height, so we're gonna do the y function and we're gonna plug in 2.34. Okay, so take your y equation, -16, 2.34 and square it, plus 75, 2.34. So if we do the math on that, we will get 87.89 feet. So at this moment, the y value is 87.89 feet, okay? How far did the ball travel? Now that's an x value. So that is finding the x value when the t value is 4.6875. So we'll plug it into the equation. 75 root 3 times 4.6875. It's going to get 608.92 feet out, which kind of jives with our picture, right? This was 608.92. And this was the height. So this value corresponds with the height right there. This value corresponds with the distance out there. And t is not on the graph, it's working behind the scenes.